We use our smartphone every day. But, have you ever wondered how your smartphone charger works? You would know that charger converts AC to DC, but it's not that straightforward. First, it converts AC to DC, then again back to AC, and then finally to DC. Today we are going to see how the charger does this. And why are there intermediate steps? This is a normal charger that converts 220 volts AC to 5 volts DC. Let's see what's inside. Now we can see all the electronic components used in it. There are diodes, capacitors, transistors, and resistor. Also, there are resistors below the PCB. This is a transformer, and this is an optocoupler. Once power is supplied, it turns on. To understand it better, let's rearrange the circuit. Now we can see all the components and connections. This red wire is phase wire and the black is neutral. First, we have is a resistor. By observing the color bands and reference table, we can see it's 260 kiloohms. This is a fusible resistor which prevents damage from overloading. Then there is a bridge rectifier made by 4 of 1N4007 diodes and a filter capacitor of 450 volts and 2.2 microfarad. This circuit converts AC to DC. This is an oscillator circuit. This converts DC back to high-frequency AC of 15 to 50 kHz. We can see the values of the components. This is transistor S8050. This is its pin configuration. And this is transistor 13001. This is its pin configuration. This is a diode. It looks like Zener diode, but it's a fast-switching diode 1N4148 and a capacitor of 50 volts 22 microfarad. This is a AC to DC converter for the phototransistor in optocoupler. It forms a circuit like this. This is the transformer. It has 3 windings, primary, secondary and auxiliary winding, wrapped around the core. It is used to step down the voltage. The auxiliary winding is used to run the oscillator circuit. Then we have a Schottky diode 1N5819 with a capacitor of 10 volts 470 microfarad to convert AC to DC. And a LED for indication. Also, there is a feedback circuit that consists of an optocoupler PC817C and 4.2 volt Zener diode. This is an optocoupler. It is used for transmission of signal without contact. On the right side we have is an infrared LED and on the left is phototransistor. When the LED turns on, its light turns on the base of phototransistor, turning it on. This capacitor is of 102 nanofarad used for safety purposes. It is connected between primary and secondary grounds to stop electromagnetic interference. Let's turn it on and see in action. The green wires carry the positive voltage, and the blue wires carry the negative voltage or ground. Also, we can see the voltage in the circuit on the graphs. We have the input of 220 volts 50 Hz AC. This is a bridge rectifier. It converts AC to fluctuating DC. As we can see, this fluctuating DC filters from the capacitor and becomes almost pure DC. We can see we have is DC in the circuit. Now, this current passes from the 2 megaohm resistor to the base of T1, turning it on. This transistor isn't fully turned on because of the resistance, it turns on partially. Due to partial turning on of the transistor, a low current passed from the primary winding of the transformer. This induces a low voltage in the auxiliary winding. The induced voltage now charges the capacitor, and then the capacitor fully turns on the transistor. As the transistor is now fully on, it allows the current to flow through itself. Now, this turns on the transistor T2. This shunts the base of the T1, turning it off. As the T1 turns off, the flow of current to the T2 is cut off. Now the current flows to the base of the T1 and the cycle repeats. This happens at 15 to 50 kHz, which is 1,000 times faster than the rectifier circuit. Hence, you would see that the rectifier circuit is stopped. At the same time, the voltage from the auxiliary also turns the diode on and charges the capacitor and flows to the optocoupler. This diode and capacitor convert the AC from the auxiliary coil to DC for the optocoupler. The current is also induced in the secondary winding. This is converted to DC by a Schottky diode and a filter capacitor. It is indicated by the LED. But what if the voltage is more than 5 volts? Hence we have as a feedback circuit. As we reach 4.2 volts, the Zener diode turns on, allowing current to flow to the optocoupler. It also drops the voltage by 4.2 volts, hence the LED of the optocoupler doesn't turn on. The LED requires 0.8 volt to turn on. When the voltage reaches more than 5 volts, this turns on the LED of optocoupler. The light of the LED turns on the phototransistor of the optocoupler, allowing the current to flow to the transistor T2. This turns on the transistor T2, shunting the first and stopping the flow of current in the primary winding. Also, the voltage in the secondary side of transformer drops below 5 volts, turning off the Zener diode and optocoupler, and the circuit continues to run normally. Now you would have the question, why not directly convert AC to DC than this? This is because, for the normal power supply, which is at 50 Hz, the size of transformer and the capacitors are large. They cannot be mounted in a small charger like this. Hence, in the charger the 50 Hz frequency is converted to 50 kHz. This reduces the size of the transformer and capacitor required in the circuit. So to change the frequency of AC, first we have to convert it to DC and then again back to AC. Now you know how the charger that we use daily works. Thank you for watching.